let's go ahead and start off our first for this academic year of the Climate, People, Environment Program Seminar Series. So I'm happy to have many of you here. I'm going to make a couple announcements before we start, because they're going to change a few things about the seminar series if you haven't seen the emails. So first of all, my name is Ankur Desai, if you don't know who I am. I am this year's Reed Bryson Professor of Climate, People, and Environment, and therefore the person who is in charge of the seminar series as well. So I am more than happy to take recommendations, nominations of people you know, either on campus. We do have the opportunity to bring about 5 to 6 speakers a year from off campus as well, depending on funding. And so if you have people you think would be great speakers for this fit, as you know, we span everything from just kind of basic fundamental climate science, but also all of the allied disciplines looking at the interactions between climate and environment, or climate and people, or if you're one of those superstars and you do all three, then we really want you here. So please let me know. Fall schedule is pretty full, but we do have some dates, 2 or 3 dates in the spring, and then of course I'm already thinking about a year from now, especially with speakers we're trying to schedule who may have difficult schedules. Please send names to me. I'm always looking for great speakers, everywhere from early career to senior scientists. Think broadly about diversity of speakers that we can bring in as well. I want to try to keep gender parity in the speaker list as well, so let me know and I will work on it. To kick off, we have our 2 speakers today are going to go back to back, and they're going to be 2 of our 4 awardees of what's known as the CPEP Seed Grant. So another aspect of the CPEP program through its endowment is being able to support small research awards to CCR affiliates and faculty, and CCR researchers. And this allows us to expand the scope of our research to try out pilot projects. We'll hear these 2 talks will kick off our fall semester, and then the other 2 awardees will kick off our spring semester CPEP seminar series. Other announcements I want to do, I do want to make sure, so as you know, there were no coffee and cookies today, and that's because I want to create a new tradition here, which is to try to do a post-seminar reception. So anytime there's a CPEP talk, Aaron has very lovingly set up with Union South catering over at the Set, which is the bar across the street. And we will invite the speakers as well as anybody else. And I'll say you don't even have to go to the talk necessarily to come to the happy hour, but prefer that you do. I will be there, and if I'm in a good mood, I'll buy the first round of beers, and hope there'll be some food and snacks as well, brought to you by CPEP. And so please do come. I hope to make this kind of a regular CCR and CPEP social event that we can use throughout the year as a way just to get together and talk. I always find myself, when I'm a speaker at other places, I really like receptions after talks, because it's usually a good time when people actually have questions about the talk you just gave, and a good way to kind of continue. Plus, you're not nervous anymore because you finished giving your talk, and that makes the beer much more tastier. Another tradition I'd like to begin also is feel free to ask questions as you know, whatever the speaker recommends or suggests, either during or after. But I would like to encourage and try to get more students to speak. And so one of the things I'd like to do is that when we do questions and answers, I will try very hard and would very much want to prioritize that the first question come from a student or postdoc in the audience. And we can be here in silence until that happens, but that's going to be our goal. I'll try. And then the other thing I want to do is just open it up. Before we start every seminar, I just want to, if there's any quick CCR Nelson related or announcements or anything like that from the room. If anyone's got one. Anything cool? Any big awards, fun stuff? Larissa has pictures from Costa Rica from a field experiment. OTREC, yeah, I want to see those. Come to the happy hour if you want to see some of those. Okay, so with that, let's go. So first up is going to be Professor Dan Wright. He's a faculty member over in Civil and Environmental Engineering, and one of our favorite CCR faculty affiliates who's often in this building because it likes to think about things that we also like to think about. And today's talk is Extreme Rainfall Multiplier, an intuitive metric to quantify and communicate tropical cyclone rainfall hazard. I'll let you go, and then I'll introduce Dave after you're done.
All right, thanks. So let's see. So feel free to interrupt me along the way if you have any questions, I guess. And you know, if you don't know anything about the sorts of things that I work on, it's sort of all things extreme rainfall, flood related. We do a lot of satellite remote sensing work on the applications, landslides, and I think that's about it so far. What I'm going to talk about today is probably, from a scientific standpoint, the simplest thing I've ever worked on, and probably in the fullness of time will prove to be one of the more complicated things that I'll ever work on, if this goes as far as I'd like it to, and you might get a little bit of flavor of why that's the case. This is mostly the work of my PhD student, Chris Bosma, and we have a couple of collaborators who I'll point out at the end of the talk as well. Okay, so let's see. So recently we've had a couple of tropical cyclones that have really highlighted the need to think a little bit harder about communicating the hazards posed, particularly by the rainfall. And those are Harvey and Florence. And just as an aside here, I also had on the original version of this presentation a joke up on this slide about Sharpiegate as another forecast-related communication issue, but that story seems to be getting less and less funny as time goes on. Okay, so with Hurricane Harvey then, obviously very much unprecedented rainfall, and so as this New York Times headline pointed out, then there were struggles even figuring out how to talk about it, right? And so one of the things that ended up happening was both experts and the media moving towards this sort of language here. So 500-year flood, 500-year rainfall, right? And so I'll say a little bit more about some of the issues that crop up when you try doing that. And then Hurricane Florence highlighted a couple of other issues where, similar story, a whole lot of rainfall. The storm was steadily downgraded in cyclone category as it moved towards landfall, and eventually making landfall as Category 1. And so one of the things that ended up happening as that downgrade was taking place was that this incorrect perception developed, at least with some members of the public, that the risk associated with the cyclone was dropping, which was not really true. And so the Washington Post then pointed out that this reveals a flaw in the Saffir-Simpson scale, this Category 1 through 5 scale that most of us are familiar with. And so I'll say a little bit more about that. And then, the other point is that as people in this building have been showing us recently, these slow-moving storms like Florence appear to be becoming more common, and may in the future become more common still. And so that increases the issues related, potentially increases the issues related to the rainfall threats posed by cyclones. Okay, so then if we're trying to talk about rainfall, and this is whether it's cyclones or any other type of storm, we have some different options. So one, of course, would be to talk about an amount of rainfall. And so there you see a statement from the National Hurricane Center about Hurricane Harvey. And that's fine, although I'm not necessarily sure that so many members of the public really have a sense of what 15 inches or 40 inches of rainfall really means when it comes to what sort of risks they might be facing, right? And so, the other option then, which we alluded to before, is talking about these things as recurrence intervals. So, the 100-year storm, for example, is a rainfall event that has a 1% chance of happening in an individual year. So that's the 100-year recurrence interval or 100-year return period. And so that's really commonly used in hydrologic engineering for design purposes, for example, and has periodically been co-opted as a communication tool for better or for worse. And the for worse parts I'll hit on here. So, what are the issues with this recurrence interval language? Well, recurrence intervals are not forecasts, right? They're expressions of probability. Probability is generally not well understood by members of the public, and it would appear even by undergraduate students regularly. And so that's an issue. It describes at least the way it's usually used, it's describing the probability of rainfall at a particular point. If you're basing your estimates of recurrence intervals on rain gauge observations, or perhaps over a grid cell if you're estimating recurrence intervals from a gridded data set. But it is not describing the likelihood of events over, for example, some region. It's tied to a specific location within that region. And I don't know if that's clear to you. It's definitely not clear to the public, and it's not even helpful. So you could explain it, but you haven't really gotten anywhere. And then there's this issue of it's tied to specific durations, right? So any extreme rainstorm has its own characteristic time scale at which it is most extreme. So Harvey, at least by Texas standards, was not particularly extreme in terms of the 24-hour rainfall totals that it produced, but it was unprecedented at the 72-hour scale, right? And so then, if you want to start talking about, durations of rainfall in a public, message, that's not going to go very well because you just go off into the weeds. Another example I'll show by way of example here, another issue. So this is a map that I produced with the help of some colleagues at University of Iowa. So this is rainfall based on bias-corrected dual polarimetric radar for the August 20th storm. And what you see are a couple of isolated pockets of rainfall west of Madison on the order of about 14 inches. And so that 14 inches over that period of 6 to 8 hours is probably north of a 1,000-year recurrence interval event. But if what you care about instead was the lake level flooding issues, what really matters then is how much rain falls within the Yahara watershed. And so if you look at the watershed upstream of Lake Monona, that's about 4.5 inches averaged over this area, and that's about a 20-year event. So good luck trying to explain to somebody that a storm was both a 1,000-year storm and a 20-year storm. It's not going to work. And so I would say don't even try. Okay, so then back to the tropical cyclones. What we do these days is the Saffir-Simpson scale, right, that 1 through 5 category. It's based entirely on wind speed. But of course, the rain and storm surge and perhaps even other things are also important hazards here as well. And that's highlighted by the fact that 6 out of the 10 most deadly tropical cyclones in the US over the past 50 years were category 1 or weaker. And the fatalities in those cases were mainly driven by freshwater flooding due to the rainfall from the cyclones, which is not at all represented up here. And then on top of that, so it would be fine if there was a perfect correlation between the rainfall and the freshwater flooding and the wind speeds, but there isn't. And there can be very different geographic locations between where the maximum wind speeds are and where the maximum rainfall is. Okay, so if we were to take a step back and try to do something different, what would an ideal metric for tropical cyclone rainfall hazard look like? And so very broadly speaking, it should accurately characterize the rainfall hazard. And so Saffir-Simpson does not appear to be doing that, and there are other metrics of hurricane strength out there that, that don't appear to do that either. It should acknowledge the fact that extreme rainfall is different in different places. So, 100 millimeters of rain in a day in Texas is not that unusual, at least southeastern Texas. 100 millimeters of rain in Nevada is pretty unusual, and that's important because both the built infrastructure, but also the natural river systems, even the soils in Texas have evolved to deal to at least some degree with that amount of rainfall. In Nevada, they haven't, right? And then you would want to be able to deal with this issue of, that idea that storms have their characteristic time scale at which they're most extreme. And then you really want to be able to have a metric that somebody can relate to in some sort of way. So I won't go into the details here, but one thing is, can we tap into cognitive processes or biases? And so one of those that we try to get into is this idea of anchoring. So well, both anchoring and using one's personal experience. So I can say a little bit more about that later if you like. Okay, so I'm going to show you the metric that we think ticks those boxes. So what we're going to be showing here are results from a 70-year-long gridded rainfall, gridded rain gauge-based rainfall data set over the southern and eastern United States. And basically what we're just doing is overlaying that rainfall with tropical cyclone tracks since 1948. And we have about 400 storms over that time period that we can study. Okay, so this is the metric, this extreme rainfall multiplier. It's very, very simple. You take your forecasted or observed tropical cyclone rainfall of a certain duration and divide it by the 2-year rainfall of that same duration. And so here, for example, we have 600 millimeters of forecasted or observed rainfall divided by a 2-year rainfall of 120, and you get an ERM of 5. Okay, so then this tropical cyclone is, the rainfall is 5 times larger than that of a 2-year storm for that location. Now,
and the 2-year storm is over 24 hours? Or?
It depends, so they have to be of the same duration. I'll show on the next slide something, I think it's the next slide, that might make it a little more clear what that actually looks like. But yeah, that's a good question. So why the 2-year rainfall? Well, so the technical definition of this would be basically the storm that has a 50% chance of being exceeded in any given year. But the more important part from the communication standpoint is the less formal definition, which is, this is really a typical heavy rainstorm for a region, right? So anyone who's lived somewhere for more than a year or two is going to have some sense in their mind of what a typical heavy rainstorm is like. And so you're expressing this cyclone or the rainfall from it in terms of something that they're more experienced with. Yeah.
What's the size of the grid that you're talking about in that first bullet point there?
Yeah.
How many regional, what's the region in that definition?
Yeah, so that's a really good question. So this is written up in a paper that's in review or in revision right now in BAMS. And in that, we're doing this all at the quarter degree by quarter degree scale. So that's the grid size of this data set. You could certainly think about integrating over some larger area when you do this, and that's kind of left for future work. But at the moment, it's roughly a 500 square kilometer area. You could do it with point observations or much larger areas, all sorts of things to sort out there. So this, I think, gets at this question of the duration part. So here you see, if I'm not mistaken, these were the 3 largest events in terms of ERM from our data set. And so we've got Harvey, Georges, Floyd, and you can see actually that each of these storms had a different characteristic timescale at which their rainfall was most extreme. So this was daily scale data, so we couldn't get any finer than that, but Harvey was most extreme. It had its highest ERM value at the 3-day duration, Georges at the 2-day, and Floyd at the 1-day duration. So basically, if you were going to then communicate this, you might want to pick that maximizing value and use that to describe this. Just as a basic sanity check, all 3 of these storms were billion-dollar disasters, in some cases much higher than $1 billion, and all did produce fatalities. So the fact that our top 3 events corresponded with storms that did actually produce some major impacts is at least a first cut look at whether this matches up with reality. And so this just shows some basic summary stats. So overall, the mean ERM from our data set is about 2, so twice as large as a 2-year storm for that location. Some correlation certainly between lifetime of the storms, or the duration of the storms, and the ERM values. So this is really, the big storms that park over a place are going to dump a lot of rain and have longer durations. And then there's, somewhat of a relationship as well between Saffir-Simpson scale and ERM, although not a super strong one.
What are the colors?
What are the colors? I think it's just colored by, this was my students plotting, so I don't know exactly, but I think that it's just darkest would be the highest value of ERM, so I'm not sure that it's actually showing something super necessary on this particular plot. He loves making really
Okay,
nice
I see.
looking
So there's
figures,
just box plots and then
yeah.
all the individual points are colored.
Yeah,
Okay.
okay.
I think your next slide is going to be a map, but I was curious about really, really dry places. You got a divide by near zero problem maybe with this?
Yeah, I guess I'm not too worried about it.
I mean, if you're focused on tropical
Yeah.
cyclones, it's probably not, but
Yeah,
you're using
yeah.
this for, say, southwest monsoon or something, right?
Yeah. I mean, I suspect that pretty much everywhere in the U.S. you're going to have something non-zero for the 2-year rainfall, but maybe there are a few
Yeah, I don't
exceptions
know,
to
I'm
that.
just curious. Yeah.
Yeah.
Did this include East Pac? The East Pac cases? I'm trying to remember if we had looked at East Pacific landfalls.
No, this
So
is
that
just,
probably gets at your, I don't think that we're looking at the Southwest US
Sure.
events.
Right.
yeah, this is just North Atlantic
Gotcha.
Basin.
North Atlantic.
Okay, cool.
Yeah.
The other thing I was just going to mention is that this correlation with TC strength is interesting because previous work, I think, has shown almost no correlation
Yeah,
with
Well,
the Saffir-Simpson scale for rainfall.
yeah.
But putting it in this context, there's at least perhaps a weak relationship.
Yeah, I actually don't, I think that at some point Chris had just run a correlation, a non-parametric correlation between the two, and I don't remember what that came back as, but it was not overwhelming by any means. I don't remember if it was significant, or, I'm not sure. But yeah, I mean, this normalization does some interesting things, and I think more thought has to be put into whether those are important things or not, yeah.
So that bottom thing is saying that the categories kind of are correlated? They are correlated with the
Slightly, although, I would need to look a little more into it to see what an actual correlation coefficient or something would look like. This, to me, doesn't look that strong,
Okay.
but, yeah, I don't know what quantitatively that looks like.
Sure.
That's a good question. I should ask Chris to
Sure, you
verify
could
that.
compute the variance explained by the category versus the variance explained by
Yeah.
the
Yeah.
metric you're using.
Yeah, exactly.
Then
Yeah. Okay, so this map is showing, so first of all, it's showing our study domain here, so we're not looking at the western US, for example. But, interesting things pop out when you normalize by this 2-year rainfall. So you can get really high values of ERM scattered, throughout New England, and then, of course, Harvey and other events in the Texas Gulf Coast as well. And I'm not showing it here, but we've done some analysis where we basically conclude that the distribution of ERM over this area really doesn't vary regionally. So in other words, the distribution in the Gulf Coast is the same as the distribution in the North Atlantic, or in New England rather, which is interesting for a couple of reasons that I might not get into in too much detail here. One thing that we haven't spent much time on is the issue of trends. So you could, if you wanted to, run a trend analysis on these ERM values, and so we did that, and you don't find a significant trend, although it's a little bit, I racked my brain figuring out exactly what that means and how much we should think about it. One thing that is important is that this denominator is non-stationary. And so what we've ended up doing, at least for our BAMS paper, is adopting a climate normal sort of approach, 1981 to 2010, 2-year rainfall. But I think yeah, like I said, there's just more to think through on this aspect of it. And also, whether you could kind of use that normalization factor in a forward-looking way to, you might think, well, we've got a better shot at knowing what the 2-year rainfall is in 2050 than the 100-year rainfall, so can we use this to actually rescale events for the future? But that is basically something I thought of about 30 seconds ago, so I'm going to stop there. Another thing that we played around a little bit with is linking ERM and recurrence intervals together. So here you see the fit of an extreme value distribution to our data set. And then, so, we can find things like an ERM value greater than or equal to 4 having a recurrence interval of roughly 3 years. Harvey having a recurrence interval of roughly 100 years. The key point here, though, is that this is interpreted a little differently than we typically do when we talk about recurrence intervals, because here we're talking about a regional exceedance probability in the sense that, what's the likelihood of something like Harvey happening somewhere in the United States, or at least in that study region I showed a few slides back, not happening in Houston specifically. Okay. And I think in the long run there may prove to be some useful properties to come out of this, whether it's for statistically based forecasting or for a long-term hazard and risk type work, because basically, well, in the interest of time, maybe I won't go there, but interested in seeing where that goes in the long run. We've also spent a little bit of time thinking about this in the context of forecasting. So this shows ERM maps for 2 different forecasts for Hurricane Florence on September 12th and September 14th. And we basically just made these to show what it would look like. And in this case, the underlying precipitation forecast was quite accurate. And so we ended up with a 3-day ahead ERM forecast on the 14th of 5.7 and an actual of 5.8. But of course, that has nothing to do with us. That has to do with the quality of the of NOAA's forecast. Right now, we're just starting to look at this globally using a satellite precipitation data set and the International Dust Tracks database. So I won't go into too much of this, but basically the idea is, we saw that over the eastern US, there doesn't really seem to be differences in the distribution of ERM. Is that true globally? I'm not sure, although certainly some spots end up popping out, like off the west coast of West Africa and in the Arabian Sea, that suggests that it might not be true, although I have to throw some statistics at that to figure out if that's really the case or not. Okay, so just to summarize then, we've got ERM. We think that it is characterizing the rainfall hazard, broadly speaking. It's able to identify both locally and nationally extreme rainfall events, and we hope anyways that it has a simple meaning that can be related or anchored to individuals' personal experiences. And then just going forward, we want to do some work looking at the geospatial and geotemporal properties, which I think are important if we wanted to use this in sort of statistically based forecasting or long-term hazard and risk work. Work on the messaging part of it, and then putting together a catalog of these past events so that during in a forecast situation, let's say if ERM 5 storm is approaching land, you could go back to your existing catalog, pull out all the ERM roughly 5 storms, pick a few, and actually look at the impacts that they cause in terms of flooding and economic damages, etc., and take those to the public as examples of past history with similar events. So I just want to acknowledge the variety of funding that we've had on this, and our collaborators both from this building and from a couple of other universities as well. Thanks.
Thank you.
Questions, but maybe while we're switching over, if there's any other discussion.
Is there a reason to focus just on tropical oh, sorry.
Oh, it's okay. There was one in back end.
Thanks for the talk. So I have a question. For example, for some natural disasters such as cyclones, we have multiple points of hazard, such as wind and rainfall.
Yeah.
So like the old-fashioned indicators focus on wind, and you're focusing on like rainfall.
Right.
Types of hazard. Is there any way to kind of have levelization or normalization of those indicators together to come up with single point data for communication and for risk analysis, etc.?
Yeah, I guess I would say probably. I haven't really given that too much thought. I know that there has been some work done on trying to come up with multi-hazard metrics. I think one of the issues that hasn't well been thought through with that is this idea of tying it to the local environment, right? So, buildings in Florida are going to be able to handle high winds much more so than buildings in, the New England, for example. But that doesn't mean that you're not going to have wind damage in New England from even a lower category storm. And so, what we're doing where we're normalizing by that local 2-year rainfall, I think is probably a useful general way of thinking about moving forward with a multi-hazard metric so that you can make sure that it's really describing local conditions rather than something else. Yeah.
Last question, Marissa.
Is there a reason that you only focused on tropical cyclones?
No, not really.
Just
Other
as a
than,
starting point?
well, so we were working on this before Hurricane Harvey from a slightly different standpoint, and the metric was a little bit different, and the purposes were totally different. So it was a different project, I suppose. But while Harvey was going on, I remember having a meeting with Chris, and we were both just like, let's do cyclones.
Okay.
All right.
So
Let's switch, there'll be time afterwards as well, questions. But our next talk is our next CPEP Sea Grant Award awardee, and that is Dr. David Lorenz, who is a scientist here in the Center for Climatic Research. And keeping the theme of precipitation, but also moving into some other ways of looking at the system, we're going to hear about statistical downscaling of daily precipitation and temperature, probabilistic approach, which is probably what I would expect.
Thanks, Encore. Yes, so probabilistic approach is a key word here because I'm going to argue that really that kind of approach is really the only way to really get a downscaling, statistical downscaling that has proper extremes and other features too that are realistic. So what is downscaling? So we have global climate models. They need to cover the whole world, cover the oceans too, because things are all coupled. So because of that, they're kind of coarse resolution. And so if you want to know what's happening at the local scale, you need to perform some approaches in order to take the large scale and output local scale weather data from that. One way is dynamical downscaling, and that's where you embed a higher resolution model. It's sort of like a global model, but just regional, and to integrate the dynamics. And the other way is statistical downscaling, which is what I'm going to talk about here. And that's basically, you have the large scale and observations, ideally a long record of that, and you find statistical connections between the large scale and the small scale. And then you would apply that to climate model data to generate small scale weather from the climate models. So this gives sort of a slide, shows sort of the nature of the problem here. So this is the NCEP reanalysis, but effectively for our purposes that's a climate model. And so this is the precipitation on a certain day, I think in July, and this is the observations of precipitation for that same day. And so you can see if you blur your eyes, this looks sort of reasonable, but there's much fine scale structure in the observed field. And so when you're doing downscaling, one approach would be the correct for boundary conditions like topography and vicinity to the shorelines and things. But a lot of the structures occurring even in places where there aren't big topographic features and things. And so the other thing that you want to correct for with downscaling is a representation of physical processes that are not in the climate model, like convection. And some of that is systematic bias, but from here you could see that a lot of it is just kind of like, this is just like a noisy version of the large scale. So the noise, the randomness is a real key part of that. And so if you want to generate this kind of data, there's a component that's not determined only from this. There's a randomness or probabilistic aspect to this. So for a user, you really need to have the noise added in. Otherwise, you're going to not get the extremes. As you can see, the figure on the right is more extreme. It also has areas of no precipitation in the midst of all the other precipitation. And so it's not going to get the right thing without the noise. And so now, here's an explicit, it's a synthetic example here, but this is an explicit example of our approach. It's sort of the simplest scenario. So everyone here has probably done linear regression. So you can imagine here, this is our large scale predictor, say temperature from our climate model. And then on the y-axis is the temperature of the weather station. And you can see there's a relationship between them, and it looks sort of linear, so we can use linear regression, and we have this purple line. But if you use this answer, y equals a constant times x plus an intercept, you're not going to get the extremes. So like, for example, here, like the lowest large-scale predictor value you get is about 3. And if you take the line value from that, that means your lowest value for the temperature would be like around 4 degrees. But you can see there's lots of points because of the randomness that are more extreme than that lowest possible value you would get from just a deterministic forecast that is just the line, and that's it. There's actually much more to linear regression than what you typically think of. So really, linear regression, if the assumptions hold, then what you're doing is you're actually predicting a parametric PDF whose parameters, namely the mean in this case, vary with your x, your predictor. So when x is 10, for example, then the answer that's coming from a linear regression is a normal distribution with a mean that's given at the line. But there's a distribution, there's a spread associated with that. And then at a different x value, your PDF changes. So, and in linear regression, it's really easy to sort of understand and think about, but what I'm getting at here is essentially even linear regression is an example of a PDF that with the parameters varying with the predictors, and that's essentially the same technique that we're going to use for downscaling even precipitation, just with a modification to the distribution. So linear regression, you use a normal distribution, there's a mean and a standard deviation, and the mean changes with your large-scale predictor. It's a linear function of the predictor. And if you did precipitation, for example, you could choose a different distribution, say a gamma distribution, which is bounded by 0, because you can only have positive precipitation. And you would do a similar thing, except now you have different parameters that vary with the large-scale state. So it's essentially the same kind of thing, just generalizing regression to include more things than just normally distributed variables. So for precipitation, we're going to use a gamma distribution when when the day is wet, so when there's precipitation occurring, we get the amount from a gamma distribution. And then we need another component because there's lots of dry days mixed in with the days that rain. And so for that, we're going to use logistic regression, which is another generalization of linear regression. So it just predicts the probability that the day is wet. So here's an example from just Madison for April '94. Here's 9 days. And the blue is the PDF that I fit. So just like you fit linear regression, I fit this, came up with these PDFs. And there's two components. There's the amount, if the day is wet, and then there's also a number here that I included. That's the probability of rain for those individual days. So for this day, there's a 2% chance of rain. And because there's such a high probability of a dry day, the area under this blue curve is very small because the chances are it's going to be dry. This day is sort of a similar curve, but it's actually the probability of rain is 39%, so there's more area under there. And then this other day, the probability of rainfall is 99%, so it's almost for sure going to rain. And the distribution is pulled off the origin, so it peaks like at some non-zero, non-trace amount of precipitation. So just this gives you an example of how this PDF is varying, and the fact that it's varying. It's not we're not using a single gamma distribution. We're using a distribution that's varying day to day with a large scale. And so we have a PDF. What do you do to get data for like a user? So there's different ways you can actually do this. And one way of doing that is you have your PDF and you just draw a random number from that distribution. And this is an example here for daily temperature. And because you're drawing a random number, there's an infinite number of possible scenarios for the local scale given the same large scale. And we call those different scenarios realizations. So here's an example of 3 realizations. And you can see they're coupled for sure. They're all being driven by that same large scale, but you can see that there's also noise in there, that not all the variability is given by the large scale. And for precipitation, the degree of difference between the realizations is even bigger because there's more small-scale structure in the precipitation field. So some days, especially when they're really dry, they all agree, but especially when there's a wet day, there could be quite a bit of spread in the amount of rainfall. So what this is saying, like for example, there could be convective storms that are small scale that day, and so it's either hit or miss as far as whether you get rainfall or not. So that's one way of getting data, but then there's another way that can be useful in certain cases. So one way because we have the PDF, we can calculate the mean PDF, and we can use that sort of to transform the data into like sort of an analog of what things would occur if the climate changes, but you keep the same observed data, just sort of adjust it. And that's based on the cumulative distribution function. So what this means is that if you go up from 0, this is January maximum temperature, the value here is like 72%. So what that was saying is that 70% of days are going to have a temperature less than freezing. And in the future, given by the red line, that will go down to like less than 30. But you can use this sort of the opposite way. You could think of the median event, which is 50%, and sort of these two, where 50% crosses these two lines, it's like sort of analog days that are at the same point in distribution. So you can use this to sort of remap observations. So if you had an observed time series, and let's say that the temperature for this day is -5 degrees, you would first find its percentile that it is by going up to the blue line, and then you would find out what temperature that corresponds to in the new climate by going over to to the red line and then going down and reading off the temperature off the bottom. And so this gives a strategy of modifying an observed time series given by the blue here and adjusting it to be like the future. And an advantage of this way is that it's preserving all the natural variability, all the noise in the system. So if you want to force, say, an extra model that's really expensive to run, it could be an issue trying to find the signal out of that when you force it with a climate change scenario. Because you need to have a lot of data in order to filter out, to zero out the natural variability. So in this case, you wouldn't need as long a time series because that sort of natural component is the same, and you're just tweaking the time series to be like the future. And then another really key advantage of probabilistic downscaling is interpolation to a grid. So we're using weather stations for this, for the downscaling, and so we'd like to end up with a gridded project because that's easier to use and more continuous. But there's issues with that, and for an example here, this is just a gridded precipitation product that by a well-respected group. And what I've shown here is the 99th percentile daily precip. And you can see it's kind of splotchy, where some points have like a 3-inch rainfall amount, but then nearby regions have an extreme rainfall event that's like 40 millimeters. And so what's really occurring is that can be seen by looking at the stations. So do the same thing, but not the gridded product, but the stations, and find the 99th percentile. You can see that now this says the extremes are actually all up here, and all this low extremes over here are some artifact of the regridding. And so what happens is really that precipitation varies in really small scales. And so the data has extreme rainfall here is not necessarily the same day that an extreme rainfall event happens at a nearby station. And so when you interpolate, you're sort of blending that together and smoothing out the variability. And so one advantage of our method, though, is that instead of interpolating the values of precipitation, we have PDF parameters which vary over the large scale because they're forced by the large scale or determined from the large scale. So what we do is we interpolate the PDF parameters, and after that we can generate data, and then everything's preserved. So that's an example down here, by interpolating the PDF parameters which vary on large scales, and then doing drawing the random numbers from the distribution, then we can actually get realistic extremes.
So that's
everywhere.
For the same data, that thing on the upper left and the lower right.
Yeah, it's
Same.
there's issues with there's issues with improving this in the way that I did this, and that's because you would be adding randomness to an observed precipitation product. But it is analogous in that.
Okay, but the downscaled climate model, does that correspond to a warm scenario compared to the gridded observations?
No, it corresponds to the observation, so it should look like this. That was the target.
Okay, so your downscaling method is saying that the extremes are a lot higher in general than this
Right.
gridded observation method is.
Right, and they're agreeing, more or less with the stations. And that's because they're smoothing interpolation, unless it's like a nearest neighbor interpolation where you just choose the value of the closest station and that's it. Any other interpolation is an averaging, basically, of nearby stations, and so it's going to damp extremes because they're not doing all the same thing at the same day.
So all the data, the same data is going into both of those, though,
Yeah,
grid
yeah, this,
observations
yeah.
in the downscale?
Yeah, this is the data, and when you interpolate it straight up, you get this. If you use this to fit PDF parameters to NSET reanalysis and then smooth the parameters first and then generate random data, you get this.
That's a really big difference.
Yeah, it's massive. It's like, yeah, like this point right here, it's like rainfall is like just slightly over an inch for 99.9 percentile.
I mean, that's like factor 2 in a lot
Yeah.
of places, right?
Yeah.
Is that original, just an inverse distance weighted kind of approach? Or?
I think they did inverse weighting.
Yeah.
It,
That tends to create like weird valleys. And and I don't think it matters much. It's almost like if you were to do this, it's do the least amount of averaging you can. But then you get, when you look at it, it would look kind of weird because, you know, the stations near Madison all are exactly Madison, then you switch over to where, you know, Verona's station is, and then it's, yeah.
Is it, can you get away with linearly interpolating parameters of a distribution when you have more than one parameter and maybe correlated? I'm just kind of thinking about, because I've done things like that before and I always worry about that.
Yeah, so I did find it was best when I interpolated, like, say, the mean of the distribution rather than, say, the scale parameter of the gamut. I tried to pick things that were, I think I interpolated the mean and the standard deviation rather than the direct parameters that got out from
that makes sense.
the distribution. See, I think about more physical weighting makes it end up being smoother and stuff, yeah. So, okay, so another key thing you could do with probabilistic downscaling is spatial correlations. So like the bottom two is where I want you to look first. So this is 2 of the 4 parameters that I have for my precipitation downscaling. One of these is the probability of precipitation for a certain day, and this is the amount of precipitation when wet, and these are determined from the large scale. So they have large scale structure but no small scale structure. And so how do you end up getting this? So if you were using a deterministic way, you're basically locked in to have this kind of scales in your end product, and there's nothing really else you could do. But if there's variance besides this is the random variance, then you can add that back in and get the right structure. So basically, so spatial scale deterministic component is locked in, but because it's not everything, we still have some flexibility. And so you can manipulate the spatial correlation of the random component in order to reproduce the right scales. And just real briefly here, what I did is I used an advection diffusion equation to sort of, I had some just totally uncorrelated noise and had it force an advection diffusion equation and sort of streaked it out like observations. And so these are basically, this is observations and then sort of 8 random realizations of the precipitation based on those large scale fields and then some random component. And you can see it's sort of getting the, you know, the right kind of.
What do you attribute the anomaly in western Texas and maybe over the Sonoran Desert to the observation versus all of your forecasted downscale realizations? There's nothing showing up out there in those forecasted ones, but you got a huge amount of activity in the actual observations.
I had a gray background where the downscaling is the Rockies and east. There's a domain, I downscaled over the east of the Rockies. So that's not, and I should have grayed that out as in that's not part of the data set.
More from the geographical impact of the Rockies, you know, in that region? Or
like beforehand, I had funding to do it for the Midwest, and it was easy to extend it everywhere because it was sort of all topographically not so extreme. So I arbitrarily just did not downscale west of the Rockies. So that's just not part of the data. That's why this includes the U.S., the whole U.S. Mine, though, includes Canada, and there's no Canada there. So it's just that it's just that I should have grayed out where, yeah.
Okay.
And here's an example for a climate model. So this is the precipitation in the climate model, and these are 4 realizations. And you can see here you would tend to have larger spatial scales because the winds are higher, so you get the streaking of the precipitation. Whereas like the features down here in the southeast US where it's weaker, winds are more localized, so you get sort of things like that just by including, like say, the advection. And you can also directly calculate statistics from the PDF approach, which is kind of nice. So like you can directly calculate return periods. And then another interesting thing is you can actually calculate some more involved statistics like annual maximum precip event, which is used a lot for like civil engineering and storm infrastructure, understanding what the biggest event is. And I won't go into details, but you can actually just calculate that from our PDFs. And so this is an example for Madison of the annual max precip event, the actual PDF of that for different years. And it can vary quite a bit from year to year. So like 1999 and 2000 are given in the blue. And that PDF was quite a bit different, estimated from my PDFs here. And then the red line is far in the future, sort of how that annual max event. And usually this is something where you might have a time series of 50 years, and so you got 50 data points. And instead here I'm using like sort of all events, even the ones that aren't necessarily the annual max, to sort of get hopefully a more robust estimate of this. And so yeah, that's basically it. So the main benefits are variability, you control over spatial correlation and temporal correlation. It's more physically realistic because there's unresolved processes for sure. And you also have more flexible ways of outputting. You can have just a standard climate time series, or you can adjust an observed time series, or you could even calculate statistics directly from the PDFs. That's it.
Cool, thank you. Questions? Maybe first from early career scientists? Yeah. No questions or students? Go ahead. You should ask. Okay, nobody feels then back to Dan.
All right. We can also, as you suggested, sit uncomfortably and wait.
I think we can ease into it.
Okay, that's so Dan, what you had, if I understand correctly, is the inverse cumulative distribution function for a given event divided by the inverse cumulative distribution function for the 2-year event. Dave, what you have is the cumulative distribution functions varying through time. I'd be interested to know whether or not you could reproduce Dan's metric using the directly using the cumulative distribution functions that you're using, and whether the spatial distribution of that metric, I would presume, given your downscaling, because it's based on the large scale in the first place, would probably be smooth like Dan's.
Yeah, so the 2-year event's pretty easy, and then the other one I'd have to track, I guess, the hurricanes and find the PDFs for those particular days. It wouldn't be, I guess, that hard to do, and yeah, that would be interesting to compare.
I told Dave before the presentation that this stuff all fits together. Yeah.
It's all part of the plan. Yeah.
I have all the PDFs just there, if you want to do that, like just daily PDFs for event stuff.
Have you thought about putting out a software package for this stuff? Or is that too complicated?
There's so many steps that I don't know if it, like, I might want to watch the output of each subset to make sure it's not doing something crazy.
Think about it.
But I've been asked, and then I ended up just doing something for them. But I think that definitely would be better. It's not something I have thought about, but it would be good.
Have you thought about a company that sells this?
Good. Well, let's go ahead and move on over. We'll continue the discussion over at the set where there's a food setup, and Aaron is holding a table for us. Thank you to both of our speakers, Dan and Dave. We're on a little bit of a hiatus for the next couple of weeks, and so the next talk will be on October 1st. Val Truitt from University of Arizona will be presenting a paleoclimate perspective on large-scale climate dynamics. And so really cool stuff. She works on reconstructing jet stream dynamics and variability from tree rings. She's a tree ring expert, and so she'll be here for a day and a half. And so definitely please sign up to meet with her. But the next 2 weeks will be no talks. So, all right, thank you.
Okay.